Welcome to The Machine, a podcast from WIT looking at IT and technology and a whole manner of related things. My name is Rob O'Connor. I'm a lecturer in the Department of Computing and Mathematics at Waterford Institute of Technology, and today I am joined by Mairead Meagher, Siobhan Drohan and a newbie to the podcast, Peter Carew. How are you, lads?
Hello.
Great, Rob.
Today's podcast is sponsored by caffeine, fueling the IT industry since 1945. We are available on all the major podcasting platforms, iTunes, Spotify, Stitcher, Overcast, and I had a lovely thing happen to me yesterday. I was walking to class, walking over to the IT building here on the main campus, and a student shouted across the kind of the empty space at me to say, "When is the next episode of The Machine coming out?" And I thought he was like extracting the Michael, but he said, "No, I'm really listening to it. I really enjoy it." And he asked me if I would number the episodes. So because you just have it, so I think we'll start numbering the episodes from now on and
Great.
go back and do that. So somebody's actually listening. So thank you, student, for listening. And anyone else who's listening and wants to get in touch with us, we are on Twitter at @machine_podcast. That's about it, because I'm not a big fan of social media, so I'm trying to stay off it. So Twitter, if you want to get in touch with us, go that way, or look any of us up on the WIT website and find us there. Right, today we are going to talk about efficiency, and efficiency is described on dictionary.com as the state or quality of being efficient, accomplish something with the least waste of time and effort, competency in performance, or the accomplishment or ability to accomplish a job with a minimum expenditure of time and effort, and the ratio of work done or energy developed by a machine to the energy supplied to it, are usually expressed as a percentage. I can't read. But there you go. Right, so we're talking about efficiency. What is efficiency, Mairead?
So efficiency, I suppose, in our everyday life is trying to get something done, as you say, as quickly and in some ways as elegantly as possible. So if I can use, will I use my breakfast example?
Oh, we love cooking analogies,
we love cooking, right? So if I come down to get my breakfast and I want to make a smoothie and I want to get coffee, but the coffee takes about 10 minutes and the smoothie will take about 7 minutes. So what am I going to do first? I'm going to put the coffee on first, and while that's doing, I'm going to do the smoothie. So that's sequencing there. So I don't want to have my smoothie made and then remember I don't have my coffee. So I put the two of them on. So
the idea there is that if you were to make the smoothie, that would take you 7 minutes.
Absolutely.
And then make the coffee, that would take another 10 minutes. So it would take you a total of 17
minutes.
As opposed to,
if I think about it, I put the coffee on, and while that coffee is doing, because once I put the coffee on the hob, I don't need to do anything. So that's it. So two things in parallel now. I'm making the coffee and making the smoothie, and I'll be consuming both of them in parallel as well, hopefully. So
again, there's two concepts there that you've introduced the concept of parallel, which is things happening
at the same time,
and the opposite of that, or the kind of the corollary of that would be something that's in series, which is one thing after another.
Yes, so if I hadn't thought about it and I'd made the coffee and waited the 10 minutes and then decided to have my smoothie, and the whole thing would have taken 17 minutes.
Yes.
And nobody wants that in the morning. So for the smoothie then, I got a really good... I met somebody in the corridor yesterday and they tell me, if you make this smoothie, you will have the body that everybody dreamed of, right? So I said, fair enough. And so we have to put in 10 apples and 10 strawberries and some yogurt, all right?
Right.
So I'm going to say, I'll throw them all in. They said, no, it's different than this. This is a really good one, right? You have to put in 1 apple, 1 strawberry, 1 apple, 1 strawberry, and do that 10 times. Okay, but you also have to you have to have each of the strawberries, right? So I have a special machine for doing this. Okay, so I can plan how to do this. So the best way to do it is if I cut all the strawberries before I start, and if I I cut all the strawberries and cut all the apples so that they're all ready to go. I pick up the knife once, I do all the cutting, leave it beside. That's done. Then everything is ready. So when I'm doing the smoothie, I have my food processor and I'm dropping everything in. So I never have to pick up the knife. So everything is done really, really quickly.
Yes.
So I have two things now in the making of the smoothie. I have the preparation, where I pick up the knife, do all the preparation, leave down the knife. It's not a very heavy knife, but I have to pick it up. And there's issues like that. So I don't want to be doing that too much. I don't want to be picking up the knife and maybe the knife is over in the drawer and I have to go over to the drawer and get another knife. So I do all that preparation. Then I go and I have my little loop of putting in the apple, putting in the strawberry, putting in the apple. And the point is, if I have the apples and strawberries prepared when I'm doing that loop, what I'm doing 10 times can be done very quickly.
Yes.
And that's really, really good. So I'm throwing it in, and I might even get that down to 6 minutes because I've all the preparation done first.
Yeah.
And that's what we mean. There's an awful lot of planning, but there's an awful lot of efficiency in that. Because if I had decided to chop every strawberry every time, everything, all the loop, the thing I was doing 10 times would have taken probably twice as long, instead of doing it all much more quickly and having it all gone. So it's this planning and saying, I did that, it was quicker, this bit was quicker. So anything that you're repeating, just say 10 times, you have to minimise the amount of time it takes to do that bit, because you don't want to be doing anything extra every single time and messing. So this, I'm going on about picking up the knife, but there's often issues there that if something takes a bit while, in computing terms, it might be I/O or reading to a file or something like that. You only want to do that a minimum number of times. So see what's going to take you the time, what's going to take you walking over to the other end of the kitchen, and you only want to do that once. So then I'm going to have my breakfast, Rob, and it's going to be very, very nice.
It's very nice, and it took you the minimum of effort.
Minimum of effort, and it was lovely.
Right. So how would Siobhan or Peter, either of you can take this now. How would you describe efficiency? Would you agree with what Mairead says?
Yeah, I would, 100%. And one of the main things that Mairead was saying there was all the planning. And with planning comes estimation. And that's a huge part, estimating how much time and effort is going to be involved in developing something or writing a small algorithm. And it's all, that goes hand in hand the whole time with programming. You're always estimating how long is it going to take me, man hours, to write something, and also estimating how many, what clock speed is going, how long is it going to take from the clock speed perspective for a method to run as well. And like, if we look at kind of efficiency from the estimation and from the planning and from the execution side within the coding perspective, within the world of programming, we'll see that its efficiency comes into many different aspects. It's not just writing the program, it's also how you're working in the team, how you all communicate with each other, how kind of the development process is involved, what sort of approach are you going to take from the development process, what methodologies are you going to use. And then also, when you build something, you're looking at the efficiency of that running app itself. How efficient is that going to be when it's running? Is it going to be slow? Is it going to be a slow startup? And then you're looking at trying to breathe life into apps that are already running by keeping them up to date and maintained. And you're once again looking at the planning process, the efficiency and the execution of all of that. And you're, as programmers and as software developers, efficiency is, to me, the bottom line. And not only being efficient, but also being able to estimate on how well you can be, how good you can be efficient.
Okay, now Peter, we're going to bring you in on this now, and again, get your take on efficiency in a computing context or not in a computing context, whichever you wish.
Yeah, well, efficiency is really about, I suppose, doing as much work as possible with least resources possible. So resources is another thing as well as time. So in the case of computing, well, things like space, memory space, or your disk space, or it could be in case of other resources like, say, power, be it for a computer, how much power it takes to do something. The longer you require a computer to work on something, the more power it's consuming. Likewise, say, for Mairead's, food blender for her smoothie. Again, how efficient is that? So again, it's all resources in, and the idea really being, as I suppose, we're trying to do as much as possible while consuming as little as possible, which is good practice. Okay,
now I'm going to just play devil's advocate here to you and say, sure, what difference does it make? Sure, computers have gigabytes worth of data, processors, multi-core processors that run, do millions and millions and millions of clock cycles per second. Sure, what difference does it make if I use a bit more memory? And sure, I can throw another terabyte hard drive in for very little money. Why is efficiency important?
Well, the problem, of course, is with, I suppose, the explosion of computing devices and technologies, there's more and more devices competing for the same resources, give or take. We might have, and of course, for example, if I roll out, let's say, broadband and fibre broadband, there's only so much space we can deal with as such. So to a certain degree, if everyone took the attitude of, well, there's plenty available, so let's use as much as we need, we won't try to be efficient, things will clog up and slow down very, very quickly. So it's just really good practice to be mindful of how much time you're taking to take out a task, how efficient you're using the resources, and really try to see can you refactor things and adjust things just to use a little bit less, get it done a little bit quicker, and just learn from each other. There's good ways of doing certain tasks. For example, say certain forms of sequence and certain forms of setup, as opposed to, I suppose, just doing it with a little ad hoc or a little way you invent yourself, which is a great way to learn how to program, for example. But as you mature, you should learn and see better ways of doing things, just to, of course, improve things overall and be a little bit more efficient.
Okay, so we're going to get into some algorithms and we're going to talk about kind of programming and efficiency and other aspects of IT in a few minutes. But before that, I was wondering if just a thought struck me there, if any of you would have examples of poor efficiency and how that negatively impacts on the running of a system or whatever. And I'll start you off with, I had a situation on Tuesday morning. There's a class I teach, and the computer in the class that I use for displaying my presentations is awful. It's really slow. It's very old, and I'm the first in the morning, so I have to start it up. And it could be 5 or 6 minutes before the machine is actually ready to go. And it's very frustrating because I'm a lazy person and I turn up for class, at the time I'm supposed to, and then I have to sit there and I'm looking at these students waiting for this machine to start up, and it's like a kind of a slow comedy of some kind. And I find that very, very frustrating, and that's down to the efficiency of the machine has been updated, but the new operating system doesn't work as well on the older hardware, etc., etc., etc. So that's an example of poor efficiency affecting my job and making me look like an idiot in front of 40 people or so. Siobhan, you're saying you have something?
Well, you're talking about efficiency there from the hardware kind of perspective, that it's just not supporting you in your role. But anyone who has ever used the internet will always have encountered poor efficiency from a website perspective. So you'll have come across, if you've ever browsed the internet, you'll always come across some website that you're looking at and you're waiting for it to load, and generally you abandon it after a certain length of time and you move on to another website.
It's a few seconds. What is it?
There's like 40% of people will give up after 3 seconds. And I have another statistic here that 74% when they're trying to load a web page would give up after 5 seconds. That's 3/4 of the people visiting. If your website and web page doesn't load within, say, 5 seconds, you've lost 3/4 of your people. They'll probably never come back to you. So efficiency is colossally important for websites to load, just for the loading perspective for businesses.
So in that website context, what are the issues that affect efficiency and cause slow loading speed?
There could be many different things. It all depends on how. One part of it could be how it was coded. Did you use really bad coding practice and real slow methods? The way you wrote your code, that it's using too much of the processor to actually develop or to produce the web page. Or have you got really heavy content, like images coming onto it that are really pixelated, so they're really, there's loads of pixels in them, so that they're taking forever to load? Or are you doing heavy access to pull up loads of information from a database? There's many different reasons as to why a web page is slow to load. But I suppose, like every developer from a website perspective, should be aiming to have your web page displayed a good usable content within about 2 seconds. That's really where people start getting a bit kind of go somewhere else. Once they hit the 3 seconds, it's too late.
Yeah, just one thing on that. For instance, if you're designing a website, like you're saying, it's about anything that you're repeating all the time, be really careful about. So for instance, on a footer in a website, don't have a video. That automatically loads, because no matter what page on the website people go to, they have to load that video. So maybe you need to have an uploaded video on one of the pages, but minimise that to the page you need it on. And that will cut down. So for instance, you might have 20 pages on your website. It only needs to be on one. Don't put it on every one, just for the sake of thinking about it. And that's the sort of efficiency that you can, so it's much more efficient. You haven't really lost a lot, because who's going to be looking at the video anyway? So it's just planning like that really, really does help.
So, but what I'm hearing there, and I would echo, is that there's no one right answer and there's no one thing. It can be a combination of factors, or assets or whatever, that there's no one thing, but the concept of efficiency is about working smart. If I could be, go on.
And just one other thing, like we're talking about web pages loading, so that's the efficiency of the page being actually displayed. But Google do things when you go into Google and you do a search on it. They will they search for the faster sites, and they'll be displayed first. So ones that that
They're higher
exhibit
up the rankings,
good,
is it?
ones that exhibit good performance and good efficiency for loading will appear higher up the page on the rankings. So not just from your user perspective of viewing a page, but from the search perspective of being discoverable on the internet, performance and efficiency hugely matters.
Okay, so is there any way, and I don't mind who wants to take this. So I think we've established that efficiency is an issue. It's important issue in life but in computing particularly. How can we measure efficiency? How can we say that something is faster than another, or this is a certain degree of efficiency? Is there any method for that? Any of you want to take it? Okay, Peter, you have your hand up.
Sure.
Go for it.
Well, for coding, for example, there's two ways we can approach this. We can either look at it without running the code, whereby we looked at mathematically. It's called static analysis. We just looked at mathematics behind things, and we can figure out the pattern this sort of algorithm or bit of code is likely to give us. Okay, and idea really being, of course, is that some patterns are preferable than others, and we can just figure out some, for example, are very insensitive to size, for example. Whereas others basically, really, I suppose, suffer if size gets really big. So after that, then we can actually measure by actually running the code and trying to measure it's what we call dynamic analysis. And there's a number of tools, very often called, say, benchmarking tools, which do things like, for example, try to run a task and measure a time differential, the difference between the time when a task starts and when it gets complete, usually in sort of nanoseconds or a millisecond or two, give or take. And we can try that again and again and again for a task to give an average, I suppose, benchmark of how well it performs on a certain, I suppose, benchmarked system.
Yes.
And if we were to do that, of course, we could try different approaches to solving the same task. And we can benchmark them against each other. We can figure out which ones tend to behave best.
Can I stop you there and just ask you to describe what the term benchmark means? Because you hear it a lot.
Yeah, benchmark basically...
It's nothing to do with an actual physical bench.
No. It's really to, for example, compare to a baseline, really. Basically, okay. We're comparing things against each other. So, for example, if we're running code on a given, say, system, well, in order to compare that code fairly to other similar code, you'd run it on the same system with the same amount of memory, the same processor. So we can benchmark things against each other in that sort of fashion. Such as just, for example, comparing to a baseline benchmark.
Yeah, so if I had a program and you had a program that by and large did the same thing and we wanted to test which was faster, we wouldn't test yours on a 2018 MacBook Pro with all the RAM in the world and test mine on a machine from 2003.
Yeah, precisely.
Yeah, because that wouldn't be a fair test.
No.
So a benchmark is about a fair test. It's a scientific test, really.
It is, absolutely.
Yeah, okay. Right, I remember from back in my programming days there was a thing called Big O notation. Mairead, I'm looking at you.
I know why you're looking at me.
Right, okay.
I was probably that soldier.
You were probably okay. Big O. I remember O and O to the power of n and logs and things like that. What is Big O notation?
Big O notation is what Peter is talking about there. It's a way of mathematically modelling how much time it will take to execute a task in a static way. So we have, if you have a data, we classically call it of size n. So you've a data set, so that could be the number of students in class, or it could be the number of books in the library, or whatever. And there's certain things you want to do with that. Now, there's certain kind of classic things we want to do. We want to search through a collection of those things. Now, that's different than a Google search. It's just that we want to go one by one through all of the items in that collection. So we want to search that. We also need to sort them, and depending on the way our data, and this depends on the data that's coming into us as well. Is it big, very, very big data? Is it very small data? Whatever. But generally, you'll want to sort data, and sorting data essentially means going through, like if we just go through a data set of size n, or we'll just say 100 or 200 or whatever, roughly if I want to do something very simple like print out all the students' names, if there's 200 students in it, it'll take me roughly 200.
Yes.
Somethings, right? Some unit of work. Now, what's interesting about that is that's we call that N of order N. So if I decide I've 300 books or 300 students, that goes up to 300. Now if I'm doing
So big O is order, is it?
it's the order, and it's roughly. And what's interesting about that is if I actually do twice as much, if I print out 2 things about that student, that's actually what's not important. So that would be like 300, just say if it was 300 students, so it would be 300 units of time. We're not actually interested in whether it's 2 by 300 or 46 by 300. The 300 is the big important. That's why we say order. So we actually ignore the 2 or the 40 or whatever. Now, if we're doing something, every time we meet a student, if we go back through each one of those students, then that becomes 300 by 300. That's very, very expensive.
Yes.
And it's bad enough when it's 300, but when it's 3 million, it's really, really expensive.
Yeah.
And that's why it doesn't matter whether it's 2 or 3. It's what we call the order of. So we have these things called nested loops. So every time you meet a student, you'd say, oh, I want to check, and I go through all of the other 300 students again, and I do that every time I'm in. So you can see what's happening here is there's a huge amount of looping within loops.
So what you're talking about is kind of an exponential growth. And again, if we
It
were
is
to
an
use it,
exponent-
I'm just thinking of an analogy that, say, Black Friday
Yes.
and all the sales
Yes.
that were online and
Yes.
elsewhere. And let's say I was on a website
Yes.
and I was looking at blenders because
Yes.
You have also taught me about this wonderful smoothie and I want
Absolutely.
to go and make it. And
Absolutely
I'm
do.
looking at blenders and I go onto a website and I search for blenders
Yeah.
and I want to order them by price because I'm a cheapskate.
Yes.
And I go to...
I'd heard that.
Yeah, oh, it's
Okay.
completely, yeah. I didn't even buy you coffee. But I want to order them by price. And let's say there's 6 blenders.
Yeah.
To sort them by price is very easy. But let's say
Yes.
I'm going to a bigger website and there's 6,000.
Yes.
So
Yes.
if it was an exponential thing, it was 6 by 6 would be
Yes.
36.
Yes.
But 6,000 by 6,000
6,000
is suddenly you're into a massive,
so then you
huge number.
start having problems. So
And that comes back to the scalability of computer systems that we would have
absolutely.
spoken about
Absolutely.
all the way along
So-
through the podcast. Yeah.
And if I can use the word elegant, because I love using this word, if there's an elegance in your original plan, it will scale up. Honestly, it will, right? And so if we've assumed, now when I mentioned sorting, because I didn't mention that, generally in computing, if we're going through a list of data, it's really useful if they're sorted. Sorting is expensive. So for us, if we're all sitting here in the studio and if we wanted to sort by ages or whatever.
When you say expensive, that's not a monetary cost. It's expensive in terms of processing
in processing and time.
Yeah,
okay,
yeah.
because it's like if you're sitting at your computer and you're 6,000 or you're whatever. So even if we wanted to sort, just say ourselves here on age, how would we do that? Probably with a lot of shame. Probably with a lot of shame. So one way of doing it would be that we'd all line up and we'd say we know each other very well, so we're not going to tell any secrets. But one way would be to say to everybody to look at each other and to swap the person beside them. And there's loads of different ways of doing this. And there's 4 of us here in the studio, and that would take very, very short amount of time. You go into a class of 40, and I think I've just found a great way of doing this. So I go into a class of 40 is going to take longer, 400 is going to take longer, and so on, right? So there's one other way that we could do it. There's an easier way of doing this, right, in the group. So if we just say height, or because I'm not going to say who's looking the oldest here, but if we say the height, we're going to look and we're going to say we'll judge by height. So we're going to scan across and we're going to say, Peter, you're the tallest, right? So we're going to put you over there in the corner, and I don't want to hear from you now anymore, Peter, right?
Yeah.
So now there's only 3 left, and now we're going to go, Rob, right? You're the next tallest over there, and you stand beside Peter. You know Peter is taller than you, and now there's only 2 of us left. So what we're doing is we're doing it differently there. Now that's still going to be expensive, but it's better than the one if we just every single time just try to kind of bubble up.
And would that be right? So if anyone looked up, what you're getting there is an algorithm, is
Yes,
a systematic way of doing something.
that.
And sorting and searching are 2 of the kind of the classic algorithms
I've made a livelihood out of it, Rob. Yeah.
Am I right in saying what you're describing there is what's called a selection sort?
It is.
Jesus, I'm doing well. I
Didn't
remember as well.
Didn't I teach him
Yeah.
well?
But that's a selection sort, and
Yeah.
in big O notation,
Yes.
that would be n squared, isn't it?
That would be n squared.
In n squared.
Yes,
So
yeah.
it's an exponential, because
an
again, for
exponential.
4, it will take,
Yeah.
possibly 16 goes to get
Yeah,
it
but
right.
it's actually a good n squared, but that's
No, I know.
Yeah,
But if
yeah.
we have 4,000, it's
Absolutely.
now 4,000
It's-
squared.
it's
and
very
if you
sad.
4 million,
Yeah,
it's
it's
4
very
million
sad.
squared. And that's the
Yeah.
thing about computer systems is
Yeah.
when you think about an algorithm, you can't think about the small example. You have to think about how will this scale in terms of
Yeah.
very large volumes of data or whatever.
Yeah.
Okay, so that's. And there's other sorting algorithms out there. There's, there's bubble
you
sort,
note your costs, Rob, I could give you
spaghetti
argument.
sort. Is there a spaghetti sort? Is that another one? I think. I think
Yes.
there's a whole load of
There's
them.
merge sort, which is
Merge sort, yes.
Please, somebody look up the merge sort and do it recursively and just have a lovely day.
Is it?
All right?
But
Yeah.
you're talking about there is an elegant algorithm,
Yeah.
merge sort.
Yeah.
So somebody
Yeah.
go and look it up, and I'm sure you can even find a video online if you don't want to have
course
to
you
read.
can.
So, or you can
Yeah.
attend one of Mairead's classes.
Yeah,
Ask
yeah,
her
yeah.
about merge sort and see her face light up. Right, but the other one then is searching, and we've talked
Yes.
about kind of search.
Yes.
And again, search is not to be. This is search through a collection of data. It's not necessarily
Yes.
a Google search, right?
Yes. Yes.
So what would be some of the classic search algorithms, and how would they compare with each other?
Okay, so if we take if I do what we call a binary search now, a binary search is the coolest search ever, right? Because if I was just thinking coming down, I always use the idea of a telephone book, but I'd say loads of people listening to this podcast just have never seen a telephone book. But a telephone book, for those of you that are lucky enough to be young enough not to know it, is an alphabetical listing of all the names in a particular phone area. So just say I wanted to look up Siobhan Drohan's name in the phone book. Okay, the way I would do using a binary search. Now I'm able to use this search because I'm looking for it in the telephone book, and I know the telephone book is sorted. So I'm using that information. So I'd probably, because I know the alphabet, I'd probably go towards the beginning of the book. But we're going to forget about that for the moment. We're going to do this purely, strictly mathematically. So what I'm going to do is I'm going to go into the middle of the book, and I'll find somebody like Mairead Meagher. All right, and I'm going to say, well, I'm looking for Siobhan, so I know that Siobhan is in the first half of the book.
Because she's D.
Because she's D, and
Yes.
D becomes before M, and M
Yes.
is in the middle. So I'm going to cut the telephone book in half. I'm going to throw away the top end because I don't need that anymore. Then I'm going to take the half of it now, and then I'm going to go into the middle of that again, and it'll be in somewhere like F. And I'm going to say, well, Siobhan D is in the first half again, so I'm going to chuck away the right hand side of the book again. Yeah. So what I'm doing every time is I'm halving the size of the data that I'm looking for.
Until
Right.
eventually you will hit
Until
on.
eventually I will go. But the really interesting thing about this is, if we look at this, right? If we look at just say there's only 32 books or 32 names in the telephone book.
Yes.
In the first chop, I get rid of 16 names. In the second one, I get rid of another 8. The next one, I get rid of another 4. So actually, the maximum number of looks I have to do is 5
Yes.
for a data set of 32. Okay, now bear with me, because this is all about the power of 2, and I could give you another hour on that. My telephone number is mostly the power of 2 things. That's how much I like the power of 2. But 32 is actually 2 to the power of
5. Yeah. Okay.
And remember, I said you only need 5 what we call hops to do that. Now, that may be not that interesting for 32, but that means that for something that's 2 to the power of 17, I just need 17 accesses.
Which is actually a very big number. I couldn't even tell you what it is. But
I-
it would be a
I-
huge number.
I'm really glad I don't know what it is, right?
Yeah,
But it's massively big. So what you're talking about is an incredibly small number of accesses to actually find. Now, of course, Siobhan mightn't be in the book, but we'll find either that we'll find where she is, or we'll find that she's not there within. In the case of 32, 5, or in the case of 2 to the power of 17, 17 times. And that's incredibly efficient. And we call that log n. You know, there's a because that's 2 to the power of, n, and it's log n for any of you that are interested in that.
And an inefficient way would be to just start at the beginning
Start
and
at the
search
beginning,
through
yes.
everyone until you got to
Yes.
Siobhan Drohan. In which case,
Yes.
you might, because D is towards the start, you might get it quite quickly. But if
Yes.
it was,
Yes,
you know,
absolutely.
Zachary
Yes.
Zebedee,
Zebedee,
it would
absolutely.
take you 32 bits,
Absolutely.
32 goes to get there,
Absolutely.
and that's not very
Absolutely.
efficient.
Or it would be like going through and I've often, don't ever go through a telephone book just with a number. With a telephone number.
You'd be
and
a
try
long
to
way
find
looking
it.
for that.
It's a
Yeah.
very, get in the hobby. Don't do that, right? Yeah.
Now, right, Peter, before we began, you were actually talking about other ways of measuring. You were talking about dynamic measurement.
Yes, yeah.
So, but how would that relate, say, to programming? Is there tools or
Yeah.
methods that we can use for measuring things that isn't necessarily just a purely mathematical kind of notation type thing?
Yeah. No, different languages and different tools have their own tools and their own harnesses. So, for example, in Java, one well-known one is called Java Micro Benchmark Harness, which is a set of automation tools for allowing us just to basically, frankly, test our Java code. And it'll produce reports for us. It allows us to specify parameters like how many runs and get an average off, whether we're measuring things in nanoseconds or milliseconds. And also does little things like, for example, computers have this notion whereby they use caching. We're back to efficiency as opposed to doing everything from scratch. It tries to reuse, say, downloaded web pages. It tries to reuse recently run code, etc. So to avoid, I suppose, caching affecting our benchmark results, it has sort of a warm-up process whereby it warms up it so it has a number of dry runs run to code before it actually starts measuring. So any caching which may affect it now, is sort of got out of the way. Then we can take a number of measures of throughput, time to complete, or whatever, and report back on it. So, for example, if we were to compare, say bubble sort with, say, quick sort, merge sort, selection sort, and so forth, you'd find out, say, that a bubble sort behaves just an example of a poorish, if nice to understand, sorting algorithm, very poorly compared to, say, something like, say, merge sort, which is actually, as Mairead alluded to, is a very, very good and powerful sorting technique. And it would actually show us that very, very clearly.
I remember years ago, I was working in a place and the company or the group acquired another company who specialised in kind of code metrics, so programming metrics, and they had software. And it was very embarrassing because we used to run our code through it, and you would actually see a visual diagram, and it looked kind of like a map. It kind of looked like a map where somebody was like crossing, going back and forth, and you would see areas where your program was working the hardest and it was spending most time in, and that was the area. Then the idea then was that was the area you would go back to that particular function, that particular section, and say, right, that's the area I need to make sure is running as fast as it possibly can be. Am I using more variables here than I need to? Is there a quicker way that I can do this? And that was the way to get better code. And then you would run it again and you would see, do you have as many kind of circles at that area, or do you have fewer? And then you'd attack the next bit and the next bit until you had as efficient a piece of code as I won't say as possible, but good enough. Does that make sense?
Yeah, absolutely as well. It reminds us why it's important to, say, understand what's available for us to reuse. So, for example, to sort, I could, of course, code my own version of merge sort or something, but say, just take Java, for example. There's already a well-tried, well-worn-out, heavily tested version ready for me to use, and same for other languages. So, while it's important to understand how it works, when you're trained to be a computer scientist and a programmer and so forth, there's ready-made algorithms which are ready for you to use, and they're well tested, well tried out. Again, as you said, they're never perfect. They're being improved over time, but at the same time, to a certain degree, there's nicely efficient ones which are, I suppose, off the shelf for us to use as well.
Yeah, Mairead.
And I suppose it mightn't be a bad time to talk about when we're talking about there is not the perfect algorithm.
Yes,
because algorithms depends on with what data are you using them, in what circumstance. So, for instance, the binary search I was using there, that has to be on unsorted data. So, if you're looking at a database that's constantly changing, you can't. It's going to be expensive to keep that sorted. So, are you going to be searching all the time, or are you going to be adding extra people to it all the time? So, you have to balance that up. So, if you're only going to do one search a day, but you're adding loads of people in, then it doesn't make sense to keep sorting it because that's too expensive. So for getting the one really, really efficient search, you have to expend loads of, expensive time-wise, getting it sorted so that you can have this one expense. So it's all about trade-off, and a big thing is trade-off. You're never going to get it right. You might have an algorithm that is suitable for, as we call, nearly sorted data. So like if you're just adding one thing an odd time, some of them are good for completely randomly sorted data, very good, and reasons that we can we can reason out which is good for which when we have the basis for it, and then but the unfortunately And it's like everything in life as you get older, there's never a right or wrong answer. It's what's best in this circumstance.
Yes.
But what's really good is to have all the experience and to say, well, this is good, okay, and maybe we'll just get it going and get it working, and then see where we need to spend our time getting it better. Because yes, we'd all love to have everything absolutely perfect, but we never have an inexhaustible budget. So we need to focus our time on where it's going to matter most. And it's about going in there and solving the problem that's going to give us the most benefit. So that's using your dynamic, checking where am I going to get the best benefit, then looking at it. Because, just by not thinking it through and not even being aware when you're actually doing the specification of where the gridlocks are going to be, then you go in and you fix those. So it all helps.
And this would come back to a concept that we use a lot in programming,
Yeah.
and it would also be in other aspects of IT, and you can see it even in consumer products, which is this thing of iteration. When you often wonder why, like, my Dad would always say, why they're bringing out a new one every bloody year, why do they have to? No, I mean, there's obviously an economic reason for that, but there's also, it's because they make a better version, and they make a better version. And we have a thing, like wash, rinse, repeat. It's like the hair you when you write a program, you get it working, then you go back and you see, can you get it working better? Then you go back and you see, can you get it working better? And again and again and again, until you get it to that kind of point where it's not perfect, because concept of perfection is difficult to achieve.
But we need to look for it.
No, we look for it, but you try to get something that's pretty damn good.
Mm.
And actually, I was thinking of a quote there. There's the economist David McWilliams is going around hawking a book at the moment, and he's using the same phrase over and over again that I quite like, which is, don't let the perfect be the enemy of the good.
Yes.
And I think that's kind of
It's
true
always
of
good.
computing.
Yes, it is. Yeah, absolutely.
Yeah. Right. So finally, isn't this all a bit complicated? Is it not just enough to have it work?
Oh Lord.
Now, that's a hard question.
Well, it is, but sure, if it was just enough to have it work, we wouldn't have any good music, would we? Like it's actually, you can cut this out, of course, Rob. You probably will if you.
No, I don't think I will.
Yeah, it's just, first of all, it's a thing of beauty to get it working properly. Now, I know it's not a thing of beauty if you're up on 10 o'clock and you're trying to get a deadline in and so on, but it matters so much. It matters in the way Peter talks about is, if you don't do your bit of the work right, somebody else is going to get a gridlock on your stuff, right? It all works together. It's like a team working together. If all the bits work together, then you get a bit that works much, much better as a unit. And if you write it nicely and you love the code and you see it's lovely code, you're going to be able to change it. You're going to get the payback when you go to maintain it. As Siobhan said earlier, when you go to maintain it, it's not going to cost you too much. So when you do the update, like your dad says, why are you doing the update? It's not going to cost you that much, because everything didn't break when you went to update something. It all worked together. It all updated really, really nicely.
And for survival in the marketplace as well, like if you're developing say a program, an app, whatever it is, and you're releasing it out to the App Store, and you want that app, you're going to have to keep maintaining that and making sure that you're maintaining the level of efficiency the whole way through it. Otherwise, they'll abandon your app and they'll go somewhere else. They'll get another app from a competitor. So it always matters that you do need to have a benchmark of efficiency definitely in your app. Otherwise, somebody else is going to do it, and you're going to end up losing all your business and having no app then, please. No business.
That's very sad.
No. And am I ending the podcast on that?
I know, it's
on
not,
a sad note.
No, but so efficiency is important, and it's something
From a
that
business.
Yeah.
it's some. There's no one right way to do it, but it's something that you got to bear in mind, whether you're making a website, doing some sort of hardware thing, writing a program to do something. It's something that affects computing, and it can affect your life. Peter, you wanted to come in there.
I'd have students reflect on this rather than listen to our podcast. A musical card, greetings card nowadays, probably has more memory than a computer from the 1970s, 1980s, running banks and running businesses. Think of that. This amount of memory, literally in a greetings card or a little musical book. My son likes little musical books playing various nursery rhymes.
Yeah.
The amount of code and memory in that is vastly superior to an actual real world computer from probably late 70s, early 80s, which would have 8K of memory or 4K of memory. And the amount of work people could get done with so little code was because they were so careful and efficient with how they coded.
Yes.
They understood their machine to literally add metal. And what could be done with that technology at the time is astonishing. And to a certain degree, I think, it's almost a little bit of a shame that we're being left behind, that old school programmers with those skills and that mindset and nose for immediate efficiency. We're maybe losing that little skill a little bit. And just finish off, I suppose, on my thoughts of efficiency is, I often like the term, I think, for ubiquitous computing, new technologies and Internet of Things, the term smart dust, whereby technology is getting so I suppose, smaller and smaller and smaller, and towards nanotechnology, and there's so much more of it. To a certain degree, we need that smart dust with tiny little devices to use less power, use less memory, because we only have so much resources in the world and it's all finite, but at the same time to make our lives better and more efficient as it so happens. So we have to think in terms of things are getting smaller and going back towards nanotechnologies, doing specific tasks with tiny pieces of memory. We have to perhaps, re-employ the old programmer skills of highly efficient ways of coding, etc.
Yeah, which you can still see in various aspects of computing. You see it in kind of the app world, where you're usually working with a fixed architecture device, or games consoles, where you have to get something running on a machine that could be 4 or 5 years old, which is definitely the thing. Listen, what we might do is leave it there, because I think we've had a very fairly exhaustive chat, and we should probably be efficient with our time, so that we can all get our lunch in.
And Rob, you're paying, didn't you say?
And
no.
the coffee.
The coffee, yeah. The
Oh,
coffee,
yeah.
I'll sort you out for coffee, all right, yeah, no problem. You come up to the office, we have a coffee machine. Right, to Mairead, Siobhan and Peter, thank you very much. You've been listening to The Machine, and don't forget to check us out online. If you want to leave us a review, I believe that's lovely for the metrics. It helps to push us further up the sorting algorithms. I don't know how it works, but it does something along the lines. Okay, thanks very much.